Okay, so we have already convinced ourselves that the coupling, the elastic couplings between the atoms in the linear chain lead to a non-trivial effect. The motion of individual atoms, which is observed at sufficiently high temperatures, when everything is incoherent and correlations don't play much role, is replaced by a completely different collective behavior of the system, with the excitations representing low temperatures, long waves of compression, which essentially is nothing but sound waves. So that's the essence of acoustic phonons, which are present in any crystalline structure. This is a kind of a must, if you wish. We may also have some other degrees of freedom, some other vibrational degree of freedom, but the acoustic modes should be there. I must add that the number of those, the number of acoustic waves essentially depends on the dimensionality of the system. Generally speaking, in a three-dimensional world, we have a wave propagating in some direction, but because of the fact that the space is three-dimensional, the vibration may occur in the same direction or in the perpendicular plane. So therefore, there are three polarization vectors which characterize a typical pattern of vibrations. We are considering the simplest possible case, but the displacement and the polarization coincide. The directions simply are the same. All right, so we are convinced that the collective modes are here, and we also have solved the equations of motion and were able to linearize, linearization was adopted from the very beginning. Convinced that we attribute a different degree of freedom to different values of the momentum or quasi-momentum, and these different values of the quasi-momentum were completely independent, which meant that we diagonalized the problem completely. But it was quite instructive to get the same done at the level of the Hamiltonian. I remind you again that the Hamiltonian we have chosen, even though it is not the most representative, it of course describes the kinetic energy. Here we make an approximation. This is the part when we write down something not general, but kind of a model assumption. A model assumption that only nearest neighbors and nearest neighboring atoms are coupled to each other by wires, by springs, which cannot be true, actually. In real life, it's not like this. It would be like this if instead of atoms we had magnetic moments. Then it is well known that the exchange interactions is very short-ranged. Whereas elastic forces spread over large distances, therefore this assumption cannot be justified in realistic substances. But to us it is not that important. And to us this important point is that this is the simplest model possible. And therefore it is much easier and better to understand complicated things using simplest model. So what we can do, we would like to ask ourselves, how do we diagonalize this form? It's a simple task. We have a quadratic form in coordinate representation. It is not diagonal, cannot be diagonal because it has to describe the propagation of information. By information, I mean you make a displacement of some atom at some point and then you release it, and then this information should spread because of translation invariance. Right? So therefore, we have a coupling between n and n plus 1, and that's kind of the guarantee that we will have some kind of propagating mode in the problem. But when we are asking what the spectrum is, then of course we should be able to find out the representation on the spectrum is parameterized by well-defined. If we were in quantum world, we would say well-defined quantum number. I would say we're defined by a well-defined conserved quantities such as quasi-momentum. So what we do now, we make a Fourier transformation, which I will write in the following form. Number of particles, the mass of the particles, summation over k. K, of course, belongs to the Brillouin zone. And you remember, you know, what is that? Here you write down the Fourier transform, Q of k, and the exponent. And then you do just the same for the momentum, with the only difference that the mass goes upwards. Again, k, Brillouin zone, P of k, and I can write down precisely the same exponent, but for whatever reason I prefer to write it down here for the momentum with a minus sign. It slightly simplifies calculation, but it's absolutely inessential. Absolutely. Yeah. Don't forget that these are real quantities. Whereas the Fourier transforms are not, generally speaking. It's easier to see that the Fourier transform satisfy the following feature. They have the following feature. You agree, right? Because if I take a complex conjugate, suppose here, I change the sign in this exponent to bring it back and make a transformation k to minus k, and this is why I have this. This is an important thing, by the way. It's not as innocent as it might look at the first sight. Why? Because n takes n values. 1, 2, so forth, n large. I have n coordinates in n momentum. I have altogether 2n variables in real space. 2n real variables. Because of this relation, the Fourier transforms, the Fourier components, are not defined within the whole Brillouin zone. They are instead defined only in one half of them, because the second half is taken care of by this relation. So if I imagine a Brillouin zone, split it in two halves, the negative axis is mapped onto the positive one because of this relationship. So, therefore, if I have a Q of k, which is a real part of Q of k, was imaginary imaginary part of Q of k, I have two quantities, the real and imaginary part, in the one half of the Brillouin zone. I multiply 2 by n divided by 2, and I get n. So I have n real parameters in each complex Q of k, and I have another n real parameters for a complex P of k. So the total number of variables in momentum space is just the same as in real space, as it should be, otherwise the transformation wouldn't be unitary. Unitary means the preservation of the modulus of some vector or some, it's a property of the Hilbert space or the Fock space, whatever it is. If you have a mathematical object which consists of several components or describes a multitude of different degrees of freedom, the number of the essential degrees of freedom must be conserved. This is the property of any unitary transformation. So, therefore, it is not by chance. This is important, as you can see, right? Now, what you do, you simply plug all this, which is written here, into this equation. As simple as that. And do the sums. When doing the sums, you should take into account the following property, that if you sum from over all lattice sites. And what you are summing is the exponential of the form k minus k prime n a naught. Then the result is, who knows what the result is? Sorry?
Dirac delta function. I mean Kronecker delta.
Kronecker delta function. It's a Kronecker. Is it always Kronecker like this, what I write here? Is anyone unhappy with this theorem? Is it always like this? Or do you anticipate some exclusion for this rule? What is the condition under which you will get the Kronecker? Okay, it's a technical thing. It's a small technical thing, but it's an important thing. The point is that pseudo-momentum space is divided into brilliant zones. Let me measure k in inverse units of A naught. So therefore, this is 0, this is pi, this is 2 pi, 3 pi, minus pi, minus 2 pi. This is our brilliant zone. This is the brilliant zone. If I take another vector somewhere here, then I can reduce, I can bring it back to some point within the first brilliant zone. If for this k, I make a transformation, I will replace k to k minus g, when g is the reciprocal lattice length. You must know this, right? These 2 points, this point and this point, are separated by 2 pi divided by A naught, and therefore they are equivalent. They describe the same physical state. But this formula doesn't know that. This formula only knows that I'm summing over all lattice sides from 1 to n, and has no idea whatsoever what k and k prime are. They may even not know, the formula doesn't even know that I'm playing a game with the lattice. So therefore, k and k prime are arbitrary, generally speaking. If I know for sure that k and k prime are limited by the first brilliant zone, and this is indeed the case here. So therefore, if I plug all these expressions into this formula, I will precisely have this situation. K and k prime in a formula like this will always belong to the same brilliant zone. And then the right-hand side is the Kronecker. If the k and k prime are one of them does not belong to the brilliant zone, then instead of this, you write down this. Whatever is k prime, if the difference k minus k prime does not fit into the brilliant zone, you subtract that very g reciprocal lattice, which brings us back to the brilliant zone. And this encounters for all such possibilities. When I single out only the term g equal to 0, then I get this one. But generally speaking, I have to have all of them. So be careful. Every time you have a situation like this, I can give an example of a less trivial situation. The 1 over n sum over lattice sides, and here I have something like I, k1 plus k2 plus so forth plus km and a naught. A sum of m momenta, quasi-momenta. Not 2 of them, as in the previous case. Call all the sum like this. This k is sum of j from 1 to n, kj. The answer is, it is delta, total k should be equal to g. Even in case when when the momenta kj lie within the Brillouin zone if their number is greater than 2. You can also check it. It's another theorem. When you have more than 2 momenta in the sum, then generally speaking, even in case all of them belong to the first Brillouin zone, the sum may go beyond. You can play this game if you wish. It's a technical thing. I just simply give you a precaution and warning. Be careful. Be careful with things like this. Otherwise, it's not a big deal. It's not an important issue. So if you use this formula, then the result of your calculation should lead to the following very nice expression. It should be sum over all k's. K goes again within the Brillouin zone of independent contributions h of k. And h of k, it's easy to anticipate, is 1/2 pk modulo squared plus omega k squared qk modulo squared, where omega k, that's a separate problem, we have assumed that you have already solved it, is given by twice, if I'm not mistaken, the spring constant divided by the mass and the absolute value of the sign k a naught divided by 2. This is what you get. So this is the spectrum, exact spectrum of this model. Its low distance part, the small k part, gives you, when k goes to 0, gives you immediately S times modulus k with some expression for S. It's clear. But it's a general expression for that model. It is not generic. What is generic is the fact that this is generic, this is compulsory, and the other thing is that omega of k must be periodic. It must have this periodicity. It's a consequence of the fact that your ground state represents a periodic structure. Every time you live on the lattice, the corresponding physics must be periodic in momentum space. It's the price of the fact that your space is no longer continuous. You live in a discrete manifold of points with periodicity. Forget about the momentum. The momentum is defined to the accuracy of the reciprocal lattice vector. Right. So that's actually the shape of your spectrum. These are just the zone boundaries. K, A naught, pi, minus pi, omega of k. And here I have a nice linear dependence which curves then. So it's a part of a sine, and then it continues periodically like this. This is the region when we have acoustic modes. But in the end of the day, of course, they curve and they reach some mass. Fine. So what we have found that your energy is a sum of independent contribution. Each contribution is parameterized by the value of this quasi-momentum k. So, which means that you have expanded all your spectrum in the so-called normal modes. What is written here is called normal mode expansion. Normal means that they don't talk to each other. They're independent. As if you have expanded some vector in multidimensional space in components. Along all these axes, mutually orthogonal axes, you have well-defined values of the projections, and this defines the whole vector unique. The same here. But this is a deeper thing because this Hamiltonian is non-diagonal. It contains non-diagonal terms. Why? Because in real space, what happens is propagation. of information, of compression, of some wave. In K-space, there is no propagation. In K-space, there are states. Each state being characterized by a specific value of the quasi-momentum. By the way, this is a good example of how wave mechanics helps understand quantum mechanics. Even though we are not playing games with quantum mechanics, essentially the same construction. So this is very nice because we have obtained a set of harmonic oscillators. This is the standard expression for the Hamiltonian, the classical Hamiltonian, or a harmonic oscillator. So what? Well, I have this positive definite quantity model P of K squared. I could have fixed K and then rewrite all the expression in the standard fashion. So it's a standard harmonic oscillator. So therefore, a complicated wave propagating, well, under the condition that everything is done within the harmonic approximation, an arbitrary wave propagating in the system can be represented as a set of elementary oscillators. Each oscillator characterized or parameterized by a quantity which is K, varying within the first Bernoulli zone. And for each specific K, you have the corresponding specific value of the frequency. So your frequency acquires dispersion. It becomes K-dependent. It depends on the wavelength. The longer the wave, the lower the energy. The shorter the wavelength, the higher the energy. Yeah. So it's not a trivial harmonic oscillator with a fixed frequency. It's a dispersion. Right? So this is basically what puts a full stop to the classical discussion with all what we have said about symmetry aspects of this problem, about the Goldstone theorem, and nice things like that. But now it's high time to understand that we cannot live anymore in a classical world. We have to switch our discussion to quantum physics. Now, I briefly discussed already during our previous lecture, but let me repeat again the main argument why quantum description is necessary. The argument number one is very practical. Classically, if you are classical and wish to calculate thermodynamic properties, and then you find out that what you expect at sufficiently high temperatures is equipartition law, so the specific heat turns out to be temperature independent. Well, you would naively believe that as long as you stay classical, this picture should survive, even though it is not quite so, but nevertheless. But real life tells you that the quantities, the thermodynamic features extracted from experimental data are different. And the specific heat goals follows the T to the third law, T cubed law, in non-metallic samples, because in the metallic samples there is a contribution coming from the electrons which dominates over the contribution of the latest vibration. So therefore, for certainty, let's consider insulators, such that at low temperatures the contribution of the conduction electrons is suppressed completely, almost completely. What remains is only phonons, and the phonons give you T to the third, T cubed. This is your first preoccupation. The second is, as usual, when you start digging deeper, then you ask yourself whether or not you are entitled to think classically when dealing with a lattice. Or more generally, if you have an object, even a single object, 1 degree of freedom, which undergoes vibrations, just vibrations, harmonic vibrations, a particle in a potential world. what is the ground state from the classical physics? The particle lies on the bottom of the potential well. And it's immobile. It's at rest. Its kinetic energy is equal to 0. Now you recall that, since you have learned the basics of quantum mechanics, the next thing after the discovery of atomic spectra, perhaps, the next important thing was, and the notion of the particle and the wave, which was interrogated, was the Heisenberg uncertainty principle, which tells you that if you measure the coordinate with some error of the order of delta x, and you measure then the same for the momentum. Now you have to be a little bit more accurate. To be quite accurate, I have to square this, and then I have to average this, and then I have to write down something like, if I'm not mistaken, it should be 4 here. Maybe I'm wrong. Maybe 4 is not necessary. To me, what is important is whatever is the definition delta x understood in this pedestrian way should be at least of the order of h. This is what I know. Which means that if I wish to measure the coordinate exactly and delta x is 0, then necessarily delta p goes to infinity. When the uncertainty of the momentum goes to infinity, what is the momentum? When you measure something and you don't know with any certainty what is the value of this object, it widely fluctuates. You expect it itself is infinite. Because its particular fluctuations gives you infinity. Therefore, it reaches this value for nothing. So therefore, you cannot localize your particle in the bottom of the potential well. You can't. This doesn't work. Because if you do that, this object, this device will blow up. If you try to localize a particle here, I would prefer not to be in this room. I would prefer to be somewhere else. So, therefore, the picture of a crystal in its classical ground state, and all the atoms rest in their equilibrium positions and form an ideal lattice, is wrong, cannot be right. So, therefore, the classical description which leads to such picture should be replaced by something different. And what is different? That's a quantum approach. The quantum approach allows us to keep this expression as it is, but it enforces us to revise the meaning of the variables which enter the expression of this Hamilton function. Your momentum is replaced by an operator. Your coordinate is also replaced by an operator. Therefore, the Hamiltonian transforms to an operator. It's now a quantum Hamiltonian. So if UN is a typical degree of freedom, which has to do with the coordinate, because it's a displacement field, essentially it's a coordinate. Right? You will say if we are in the coordinate representation, then this operator coincides with its value. Actually, it's a C function. It's not an operator function. It coincides with itself. It's not contested. But then, immediately you will conclude that this must be this. It's basics of quantum mechanics. This is what we have. In other words, you impose an important commutation relation that at a given site, let's call it n, the coordinate, I can remove it if you wish, or I can keep it, the n, and the momentum have a non-trivial commutation relation, the canonical commutation relation. They don't commute, they're not measurable at the same time. They're complementary, either one or the other, not the both together. The good question is, what if I have PM? So that's where M is an arbitrary, some other lattice site, for instance, not equal to N. Right? Now here one has to be careful. Every time when we quantize, so we have this lattice sites are labeled by n plus 1, n minus 1, and so forth. So if we had a simple single oscillator, we would say now we move to the Hilbert space of wave functions describing our oscillator, because we would say, okay, for a single oscillator, we have the Hamiltonian, we have the wave function in coordinate representation. We write down something like this, when h is minus h squared divided by 2 masses, d2 dx squared, and plus mass, the mass first power, omega squared, x squared divided by 2. That's it, the Hamiltonian of the harmonic oscillator, and the wave function form a Hilbert space. And all the operators operate in this Hilbert space. And I can build up the eigenfunctions of this problem. I call it alpha. I don't want to add n is already occupied. And all the set of these wave functions belong to the Hilbert space. Moreover, they form the basis for this Hilbert space. And lots of theorem follow them. But it's one Hilbert space for one oscillator. For one oscillatory degree of freedom. Here we have as many as the number of lattice sites. So therefore, the total Hilbert space, out of V, let it be the total Hilbert space, should represent the product of the Hilbert space of the first lattice site, the same for the second lattice site, and finally, the last lattice site. It's a tensor product. It's a direct product. It's a these are completely different spaces. Things happen in quantization occurring in space V2 has nothing to do with the quantization Vn, for instance. Absolutely different. So therefore, for arbitrary n, I have to write down this. The only provide us with the non-trivial commutator if the two degrees of freedom, if the two variables, the momentum and the coordinate belong to the same Hilbert space, to the same lattice site. If the sites are different, they commute. They operate as usual numbers. That's important. That's what canonical commutation is about. Well, very good. Yes. But now we wonder, you raise unfortunately everything what concerns the normal mode expression. I can again play the same game as we did in class X by writing down un 1 over square root of n and k qk exponent, with the difference that now we have operators here. And the same, I would say, just the same for momentum. And here I have these relations. I quantized everything in real space. What is the implication for the quantities in momentum space? It's a very simple exercise to check that qk prime should be IH delta kk prime. Quite similar to what we have in real space. It's a direct, straightforward. You sit down, calculate, you immediately update this. This is already something. Okay? But this is not all, because even though we had already the expression for h of k, which I can rewrite more consistently as pk dagger pk plus omega k squared, qk dagger qk. Previously we had modulus squared, now I have to rewrite everything for the operators, therefore it's natural that you have here, we have dagger here, dagger there. I want to emphasize that whereas un dagger is un and pn dagger is pn, these two operators are Hermitian operators. As you should remember, it's quantum mechanics. Why Hermitian? Because the corresponding quantities are measurable, therefore they're described by real numbers. And for the real eigenvalues, you have to have an Hermitian operator. Right? These operators, Q of k and P of k, momentum representation, are not Hermitian. They don't have to be Hermitian, in fact. This is what has to be Hermitian, this and that, but not this and that. They again satisfy the conditions. And qk dagger is q minus k. Previously we had a complex conjugation, now we have a Hermitian conjugation. So that's the difference between quantum mechanics and classical mechanics. The structure is the same. But instead of asterisk, you have to write down the dagger. Now, the knowledge of the quantization problem for the single harmonic oscillator helps a lot. Now my question is, are you aware of second quantization for the harmonic oscillator? Did you have
Yes,
in quantum mechanics or advanced quantum mechanics?
creation.
What?
We were introduced at the end.
Yeah, no, I'm not asking whether it was in the beginning or in the end. I'm just, to what extent you know how the coordinate and momentum of harmonic oscillators are expressed in terms of the creation and annihilation operators. You know, you do. Excellent. He does. That's it. So let us a little bit go back in our memories to the problem of a single harmonic oscillator, just to fix notations. Where and how do we get information about some of quantum properties of this object? Look what we have at our disposal. At our disposal we have Hamiltonian, which contains as a parameters the mass and the frequency. Or otherwise I can say the mass and the spring constant. That's the same. How should I behave if simply before solving this problem or any other problem, simply looking at the Hamiltonian? How should I conclude what is the expected quantum parameter, quantum variable or quantum parameter which characterizes essentially quantum behavior of my system? Right? What should I expect for the first place? Psi of x, the wave function, the eigenfunction, maybe a ground state wave function, maybe a wave function which describes some excitations, varies in space. For instance, you know well that if you have a harmonic potential well, which is nothing but u of x m omega squared x squared divided by 2, right? Here you have levels. I will remind you the ground state level is h omega divided by 2, then the next is h1 3 times h omega divided by 2, then I have 5 times h omega divided by 2, and more generally en h omega n plus 1/2, when n takes values 1 to 0, 2, and so forth. This is the famous formula for the quantization, level quantization, and for harmonic oscillator. And by the way, the ground state energy is non-zero, by the way, which reflects the fact that I cannot possibly put my particle on the bottom of the well and then go to have some cup of coffee. Because if once I leave this room, it will explode, as we already know. So there is a certain quantum uncertainty which makes the particle move even in the ground state. And this is what is called a zero-point motion. The motion, the inevitable motion imposed by quantum mechanics, when the particle is not at rest, but it moves. It moves in such a way that the wave function of the ground state has some spread. In fact, it's a Gaussian. What is the characteristic length? That should have a quantum origin, because in classical physics we have nothing like this. So therefore, if we have a wave function psi 0 of x, which has a structure exponent minus x squared divided by twice psi squared, this psi should be a quantum length. It should not have any counterpart in classical mechanics. There is no analog for that. Because the very phenomenon is quantum. It's a zero-point motion. There is no zero-point motion in classical physics. There is no notional wave function in classical physics. Quite honest. Right? Now the answer is this psi is square root of this quantity. This is the quantum length of a harmonic oscillator. Necessarily, it contains the Planck's constant. So if I blindly set h to 0, psi disappears. So the wave function shrinks to a point, and the particle happily goes to the bottom without any explosion, under the condition that you can drive h to 0, but you can't. It's a world constant. There are lots of discussion on YouTube these days. How shall we perceive the world constants? Because in other universes, these values of this world constant will be completely different. Right. How to derive it, by the way? It's a good question. How to derive it? How to understand the meaning of this? How to comprehend the essence of this expression before you solve Schrödinger equation or something like this? You do the following thing. You simply take a square of this. Then you bring the frequency here. And the psi square there. And then you build up an object h omega. And then you get h squared divided by n psi squared. And now you are happy. You are happy. Because h omega is energy, and that you know. And the energy for a quantum particle is p squared divided by the mass of the order of, I don't write down 2, I don't want this 2. And typical value of p would be h squared k squared divided by m. And the typical value of k will be the inverse wavelength, the Boyle wavelength. Therefore, it is h squared m lambda squared. Here. the psi should have the meaning of the de Broglie wavelength of the particle. Right? Why? It should be like this because the momentum is h divided by some length. You remember the definition of the momentum operator, minus IH dx. So momentum here, inverse length here, h is in the numerator. Very, quantum mechanics is a tough subject. Many people believe, including myself, that not a single person in the world understands it. We get used to it. It's very hard to understand the world which has the probabilistic meaning. Because our everyday experience, I have this chalk in my hand, I can put it here, and all the processes are deterministics. And then they tell me, I'm telling you that the particle cannot be localized at the bottom. So, of course I'm exaggerating. Of course there are people who do understand. I think Richard Feynman did understand quantum mechanics. At least he invented the way how to understand quantum mechanics. And it was ingenious, I would say, breakthrough just to think that instead of having a single trajectory from point A to point B, as it is in classical mechanics, and the trajectory should be a solution of the Euler-Lagrange equation. Now, please be so kind, take into account all classical trajectories and build up what is called the path integral. And then the quantum world is a superposition of all possible classical trajectories. And the reduction to classics goes when formally h Planck's constant goes to 0. Then out of all this manifold multitude of these trajectories, only one survives, which fits into the infinitely narrow channel determined by the Euler-Lagrange equation. So it's a completely different approach, but so, the person without living completely in the classical world was able to rephrase quantum mechanics in classical terms. Absolutely genius, absolutely. Anyway, if I keep going in this direction, I will manage to finish the lecture. All right, so we now understand what is this. And therefore, if we wish to deal with the coordinate in the quantum description, we should understand that, of course, we should have an object which is square root of h divided by the mass and divided by omega k. Very similar to what we had here or here. That's the typical quantum length which should be introduced. The way it works goes as follows. If I again go back to a single harmonic oscillator, I will write down that the coordinate x is equal to square root h divided by twice m omega. This is like this. And here I have a plus a double. And then if I write down the momentum, it should be, I'm not sure about the coefficient, but now we will fix it anyway. It should be h omega divided by, h mass omega divided by 2. And here we have to have a dagger minus a. If I now check the commutator, the canonical commutator xp will go as follows. First power of h, first power of 2, the rest is cancelled. and the commutator A plus A dagger. And here I have imaginary I, I'm sorry, A dagger minus A. The algebra goes as follows. A commutes with itself, as well as A dagger commutes with itself. But A does not commute with A dagger. It is just one. That's the canonical commutator between these two non-Hermitian operators. So therefore, here I have 1, and here with this minus sign, I have again 1. Because I would have minus 1, but this extra minus will transform minus to plus, and the coefficient will be 2. And then I have 1/2 here, and then I immediately recover the desired IH. So therefore, the standard algebra consistent with the algebra of what is called the creation and annihilation operators. A is annihilation, and A dagger is creation. I'll continue, intentionally continue a little bit with a single harmonic oscillator, because with this substitution and with this expression for the Hamiltonian, you immediately conclude, you derive it for free, then you have your linear oscillator, Hamiltonian, single linear oscillator, Hamiltonian, as the following form. Then you ask yourself how to choose the basis of states, what is the corresponding space when this basis operates, and how to describe the spectrum. You introduce the particle number operator, or occupation number operator, A dagger A. And then ask the following thing, whether or not it's possible to find a set of states in which N is diagonal. By the way, notice this is an Hermitian operator, even though A dagger and A are non-Hermitian, and the occupation number is an Hermitian operator. Therefore, its eigenvalue must be measurable. It must be real and measurable. Now, there are several theorems which I cannot and should not prove for you because it must have been already done. The corresponding vectors, eigenvectors of this operator, form a basis of the so-called Fock space. So there is a Hilbert space for wave functions, Hilbert space for the standard wave functions psi of x, and there is also a Fock space. It's the space spanned on the set of vectors, formal vectors, state vectors, which are denoted like this. And these are famous Dirac's notations. This is the vector ket, as opposed to vector bra, which would look like this. Bra and ket are mutually conjugate. They overlap. Gives me 1. But the point is that the equation, the eigenvalue equation for these vectors has this very, very simple and suggestive form. It tells us, it doesn't tell us, it can be shown, proven, that the eigenvalue n, which enters this expression as well as parameterizes the states of state vectors, can only take integer values, positive, natural values, 0, 1, 2, and so forth. There is no room for negative numbers. 0 and all the positive integer numbers. And then you prove the standard theorems that all these basis states are orthonormal, and they form from 0 to infinity, they form a full set of states, a complete set of states. And then you add to this one more thing, perhaps the most crucial thing. What is the action of the creation annihilation operators on the states? So when you act by operator A dagger on the state n, it moves it to the state n plus 1. It makes a shift from n to n plus 1. And the coefficient in front is this. If you have an annihilation operator acting on the same state, it gives you n minus 1, but the coefficient is simply square root of n. So then there is an idea of the physical meaning of what these objects n. N measures the number of oscillatory quanta. Quantization means that you have something like this. You have levels. The ground state level, the first excited state, the second excited state. The number of quanta here is n equal to 0. Indeed. Oh, where is it? Yes. If I continue this and write down the energy, it will be h omega n plus 1/2. So for n equal to 0, I'm left with h omega divided by 2. This is the ground state. One quantum excited is n equal to 1. It's this level. Two quantum excited, n equal to 2, and so forth. So the level is quantized, and the quantum number has the meaning of the number of oscillatory quanta in a given state. So therefore, the creation operator acting on a given state n moves it to the state n plus 1. It increases the number of oscillatory quanta. In other words, it induces transition, say, from this level upwards. It's the step from n to n plus 1. Whereas this annihilation operator just the same in the opposite direction. But please notice that the spectrum is finite, it's limited, it's bounded from below. Once you are in the ground state, you cannot go any lower. That's the full stop point, right? So therefore, there is one important relation when we first encounter the notion of vacuum. It is defined like this. There is a state 0, or the vacuum state, which is defined, and it's not simply in this state, this takes place. No, this is the definition. This state is such a state that when this annihilation operator acts on it, it's annihilated completely, which means that the spectrum is bound. Well, whereas, for instance, if you A dagger acts on 0, then you get the state 1. You can go further and, for instance, build up such an object, A dagger to the power of n, square root of n factorial. This is for normalization, 0. We have n quanta in this state. You can call it n. This is needed for normalization. So you can build, it's a very well fine-tuned theory. The levels are equidistant. The distance is h omega. There is a ground state. There is a raising and lowering operators, and there is a occupation number operator, which is diagonal. And there is a beautiful algebra. What do you want? Fantastic. Everyone tries to reduce a complicated problem to something looking like this. Not exactly, but this is the ultimate dream. You know, the people are dreaming in the middle of the night. They get up, very excited. Oh, I found the solution. Then early in the morning, that's it. After a cold shower, you realize that the solution doesn't work. You have to work further. So you can't do everything overnight. You need at least 2 nights. It's not a simple thing. This problem is specifically simple. Realistic problems are much, much more complicated. So that was the brief excursion to second quantization for a harmonic oscillator. Now we just do the same, but for our purposes. For our purposes, we need to do everything in momentum space. So what do we do? First of all, we wish to find out the expression for the operator describing the displacement field. In fact, it's not an operator, it is an operator. I will write down the answer, and then it will be clear. Twice n omega of k. And here I have ak plus a minus k dagger exponent n. It's very much similar to what is here. If you compare the structure h divided by twice mass frequency, h divided by twice mass frequency, 1 over n is the consequence of the fact that there you had only 1 degree of freedom vibrating point. Here you have n. Therefore, this is required by normalization, requires the presence of an n here. What is less trivial is again a n plus a dagger. We have it here. On top of that, there is a phase factor, which is a consequence of the fact that whatever you have should delocalize, should represent a plane wave. For a localized oscillatory degree of freedom, no particle goes to infinity. Here, the particle can go to infinity. But this is much more important thing. That's ak and minus k dagger. K and minus k are chosen in such a way that this operator is emission. If you take conjugate, you will get ak dagger here, a minus k without dagger here, and we'll change the sign here. So when you change k to minus k to recover the sign, you will find out the importance of this minus k. Is it clear? In the similar way, you can do the same for momentum. If I'm not mistaken, it could be a mistake here. But basically, it's h m omega k twice n ak dagger minus I minus k and this exponent. And you can check the algebra. Now you have as many creation annihilation operators as many k. For each k, for each value of the pseudo momentum, you have this pair. So in momentum space, for each value of the pseudo momentum you define, roughly speaking, you have your harmonic oscillator parameterized by this value. But now the question is how to write down the algebra, which is already written here. It's very simple. If I write down k here and k prime here, nothing is going to change because two annihilation operators should commute. But if I write down k here and k prime here, then the right-hand side will be chromatic. Why? Because different k's are independent. Different k's form different Fock spaces. And the operators belonging to different Fock spaces don't talk to each other. They are not restricted by any mutual relations. So that's the algebra, which is here. Now the question is about the state vectors. Now for a harmonic oscillator, we parameterize the state with a single quantum number n. Now we have as many n quantum numbers n as many values k we have. So therefore, we have this k space. You remember that under periodic boundary conditions, different values of kj are quantized like this at some mj, and mj is 0 plus minus 1 plus minus 2. It's a Born one carbon periodic boundary conditions lead to these quantizations of the momenta. So therefore, The brilliant zone also represents a lattice on the momentum space. It's very, very closely related, closely located. Points, the distance is inversely proportional to the length of the system. Maybe in this case I should write down, yeah, but L is fine. It's n times n naught. Yes, so what I wanted to say. Yeah, so this is some value kj. Here I have some kl. Here I may have some km. Typically, the ground state should look, excuse me, not the ground state, the typical state vector should look like this. nkl, nkm, and so forth. In other words, for each value of k out of these lattice states in momentum space, I have to specify the value of the corresponding occupation number. So therefore, in each k space, I know how many quanta I have. As in the state kj, I have this amount, say 3. In this KL, I have 25. Here I may have 0, for instance. So all these combinations, all these possible combinations form a multi-dimensional space for each value of k, right? And then you say simply that if I have, and for some value of k, kp, annihilation operator, acting on this state. It's let me write down whatever it is, but what I will be basically interested in the value of this nkp. It can be nkp plus 1. Here I will write down nkp minus 1. They are neighbors. The result is very simple because we know this belongs to the same space, Fock space. This value of the momentum fixes the specific partial space. So therefore it should be square root of nkp. And here I have nothing changes for all n's, including kp minus 1 and nkp plus 1 and all the others, but in between I should write down nkp minus 1. So I single out that very site in momentum space and pretend I have only one oscillator without touching all the other things. So this operator operates as an identity operator of all the states which don't coincide, whose momentum do not coincide with kp. It doesn't act on them, doesn't touch them at all. Actually, this is the end of the story, because if you plug all what is written here into the quantum Hamiltonian, what you will obtain, it will be just this expression with the only difference. You will put the sum k, omega k, and epsilon n of k, epsilon k, it will be k here, and k, okay. It's an open operator, and some, of course, and that's all. So any state can be given. We can calculate the energy in the state. This energy is given by a sum like this of partial contributions of different, coming from different values, all possible values of the momentum. And the important numbers are these d's and k's. What is this? These are just the number of oscillators describing a particular value, a wave with a particular value of k. But this partial wave is nothing but the normal mode, which are already aware from our previous classical description. So the only thing is what we did. We took our normal mode and we quantized them. And each normal mode transformed to a quasi-particle. And this quasi-particle, each quasi-particle, is nothing but the acoustic boson, acoustic form. It's a boson particle because the statistics is boson, and you have to understand what's going on. This is essentially everything what has to do with the formal description of quantum problem. It is very compact, very convenient. It's very convenient to work with the creation and deletion operators. And let me now show you something, how to do this elementary calculation. At least I will start today only this thing. I don't need this. First of all, let us ask ourselves, what would happen if I replaced a single oscillator, not the lattice, but a single oscillator, a single harmonic oscillator into a thermal bath, which will supply this oscillator with the temperature. In other words, what will happen if I now build up a quantum statistics of a single harmonic oscillator? Well, it can be done in many ways, but the simplest way would be the following. We know that for a single harmonic oscillator, the energy is h omega n plus 1/2. If the whole system, if this harmonic oscillator is at equilibrium with some environment, and the environment is characterized by the temperature T, then I can ask the following question. What is the average thermal energy, for instance, of my oscillator? What is the average temperature, average energy at a given temperature? Or of course, this average energy, which will be the average of my H. Let me write again this expression, H omega. Here I have to write down A plus A plus 1/2. It will give me H omega, let me put it like this, n bar plus 1/2. And this n bar is the average value of A. It's the average occupation number. How shall I calculate it? Now, here is the Gibbs hypothesis. The foundation of quantum statistics goes as follows. If I have a physical quantity, which is n, and I want to calculate its average, what I need to do is to find out the quantum number in terms of which this quantity is diagonal. This quantum number is n itself. This n which is here, n which takes values 0, 1, 2, and so forth, right? So I sum over all n from 0 to infinity. I put the quantity I'm interested in, its value in the state n labeled by n is n itself. So it is n. And then I put the Boltzmann or Gibbs factor, beta En, when beta is inverse temperature. And then I have to divide everything by the partition function, because this is what required by the normalization. From 0 to infinity, simply this exponent. As simple as that. Very simple, school level formula. No deep breakthroughs, very simple. This is definition of the average. So in other words, the probability, the normalized probability is z minus 1, this exponent, and z is this denominator, which satisfies the condition sum over n double n is equal. Right. I will not do this calculation for you. Be so kind, sit down and derive it for yourself. I'm sure 90% of you know the answer by heart. It's an average is nothing but 1 over exponent h omega divided by t minus 1. It's a Bose distribution function. Bose-Einstein, which is a peculiar property. Would you please tell me where is the chemical potential? Where's an idea? The standard Bose distribution function, let me remind you, the canonical expression of the Bose distribution function as a function of energy is exponent energy minus chemical potential divided by T minus 1. Where is the chemical potential? Any idea? Or are you aware of anything else similar to what we're discussing now, where you also have kind of Bose distribution function, but with zero chemical potential? Are you aware of some other physical system which resembles this? Have you ever heard about the black body radiation? That's precisely the same situation. The reason the chemical potential is absent is because the particle number. What is the particle number is in this quantum number? It's a problem. Single oscillator, only one particle which undergoes vibrations. By particles we mean the number of quanta. These are our particles. Quantized particles are just quantized quanta themselves. And their number is not determined. It's a quantum number. The average quantum number is determined by the equilibrium condition. At a given temperature, it should be this or that. But it is not like we have a system with a fixed particle number. Because this formula assumes just that. This formula assumes that the mu is true, genuine chemical potential, which is responsible for the chemical equilibrium of your system. So you take your system, you divide it in parts, and you consider dynamical processes where the particles move from one part of the sample to another one. So in each subsystem, the particle number is not conserved. What is conserved is only the total particle number, and these are dynamical processes. If these subsystems are large enough, then there is a proof of theorem which states that the chemical potential in one subsystem and the other subsystem must coincide because of the equilibrium condition. That's exactly what the chemical potential is in this setting. When we are talking about real particles, these are not real particles, these are excitation quanta. And we are just about to calculate them. That's exactly what we want to do. To calculate the number of excited quanta at a given temperature. Since a priori this number is not fixed, the chemical potential should be zero. That's it. That's all. As simple as that. You can bring about some other arguments as well, but this is the simplest one. So this is the answer. And from this answer, you can make a very important conclusion. If omega is fixed, and then you go to the temperature, which is much, much greater than the typical energy quantum in the oscillatory problem. The temperature is huge as compared to so many. Below this level T, there we have a macroscopically large number of quanta excited. In this case, this is a small quantity. You expand this exponent, and for n, you obtain in the leading order T divided by h omega, which is much greater than 1. And of course it should be like this because, as we said already, we strongly excited our system. The number of excited quanta is huge. Now we go to another limit, to the other limit, T much less than H omega. It was our spectrum, ground state. This is H omega. This is 0, and your T is somewhere here. Well below H omega, even well below H omega divided by 2. Almost 0. But you see when the temperature is very small as compared to H omega, the exponential is huge. You forget about this one, and when you find in this limit it's n bar is minus exponent H omega divided by 2. The number of quanta is exponentially small. Okay, well, now I anticipate your question. How can it be much less than 1, but when the minimum value, non-zero value is 1? The number of quanta is quantized. No, 0, 1, 2, 3. Don't forget, it's statistics. You measure, you have an ensemble of your systems. You make millions of measurements. And you average your number and divide this total value of the outcomes by the number of your tries. And that's exactly how you should perceive the n average. It's the total result obtained divided by the number of attempts. This is why it might much less than 1. It's exponentially small. It's very close to 0. And that is not what we are after. This is not the desired result. If our system represented a set of independent oscillators, then your friend in the lab would tell you, oh, the specific heat exponential is small. But he says, no, it is t to the third. It's much smaller function. The specific heat is much greater than this. By the way, this would be the famous Einstein's model. Einstein was one of the first persons, in spite of the fact he was always against quantum mechanics in its, I would say, Copenhagen formulation. He completely accepted the idea of Max Planck about the quantum. Blackbody radiation, quantization of this radiation. He accepted and understood perfectly. Don't forget, he described photo effect. He got his Nobel Prize for that. So a person who would reject completely quantum mechanics would never be able to do it. So he was a very complicated figure, in fact. So his idea was we can quantize the system in the most simple way. Forget about all interactions. Let us single out quantum mechanics per se. Let us divide our system into a set of independent oscillators, something your colleague suggested last time. Let us put each atom in its own potential well, assuming that this is a very deep well. Each well is very deep, and you can neglect the coupling between the atoms by these wires. So your system is a set of n independent oscillators, but quantum oscillators, not classical. You will get what is written here, but only multiplied by a number of reticents. It's an Einstein model. And it does not describe reality. It is good in one respect. It does tell us that the specific heat goes down to 0. It cannot stay at the constant level. You remember classical mechanics tells us classical specific heat should be a constant, independent of the temperature. Only quantum mechanics, with all this beautiful thing like a zero-point motion and quantization of the spectrum, was able to predict the decrease of the number of phonons, consequently the decrease of the total energy, consequently if the energy decreases exponentially, its derivative also decreases exponentially. Therefore, the specific heat also decreases exponentially. So the decrease is guaranteed. The quantum mechanics was able to explain why the specific heat decreases. But the Einstein model was unable to explain t to the third, t cubed, the t cubed law. That we will do on Monday. I wanted to tell you that, perhaps you already know it, on Wednesday in the morning we have a lecture of our guest on the colloquium, and my lecture will be at 4 o'clock. You remember? Fine. Questions? Questions? No questions. All right. See you then.